Our speaker today is Professor Timothy Rupert. He obtained his bachelor's degree and Master of Science degree in mechanical engineering from Johns Hopkins University, and his PhD in materials science and engineering from Massachusetts Institute of Technology. He's currently an associate professor at the University of California, Irvine, where he's also the associate director of the Institute for Design and Manufacturing Innovation. His talk today is beneficial complexion transitions using defects to make better materials. So please welcome Professor Rupert.
Thank you very much, and thank you very much for that introduction. I was sneaky and I slightly changed my title because I realized using defects to make better materials was too generic. What I'm actually trying to do is I'm trying to change the structure of defects so that we can get more beneficial behavior. And hopefully that'll make sense by the time I'm at the end, okay? So, first question, where am I from? Don't blame you. I didn't know what Irvine was until I applied for a job there. So I grew up with you all. I grew up on the East Coast, on the east side of Ohio, went to school up here, and used to cold in the winters, okay? So I'm from Irvine now. It's in California. We all know where that is, and it's in Southern California. So if you look on a map, you want to look for the big blob near LA, and if you zoom in a little bit, you'll notice that just beneath LA is Orange County, okay? And right smack in the middle of that is the campus of University of California, Irvine. So this is an outline of our campus right here. I live right over here. Don't look me up and come find me. Give me a call first. But we're very close to the coast, and we're near some places you may have heard of. So first, way out here is Catalina Island. So we're also somewhat close to Los Angeles and Hollywood. So every once in a while, we find our way into some movies and television shows. So the Catalina wine mixer, that's who's out here, right? Students know what I'm talking about, right? And then the other thing you can notice on this map is just towards the coastline is this area, Newport Beach. So this is where Arrested Development was. This is where the frozen Bluth banana stand was. There's no Bluth stand, but there actually are frozen banana stands there, all right? But more importantly, when this guy, George Michael, went to college, he chose UC Irvine, right? So, and a great mustache, too. Okay, so that's a little bit about where I'm from. Let me tell you more about sort of the people I work with. So as a professor, I don't get down to the lab much these days and run experiments myself. Every once in a while, I do some computational work by myself. But most of the great stuff I do is really coming from the students and postdocs in my group. So this is a picture of my students last summer. We have 6 PhD students, 2 postdocs. And I just wanted to point out a few things. You can tell it's California from this picture, and there's a few sort of signals there. No clouds in the sky, right? There's palm trees in the background, but also the professor wearing shorts, right? So that's a little bit different, right? We're a little bit more laid back there. So these are the more sort of up-close version of those people that I mentioned. A lot of people have been coming and talking to you recently about computational material science, and I'm going to be spending a lot of time on that today. But my group's a little bit different in that we have a big chunk of work in computational material science, but we also do some experimental work as well. And in fact, if I look up at this picture, I can say that this group of people right here are computational people exclusively. So 3 PhD students and a postdoc. This guy right here does some computational work himself too. But at this other side of this plot, or this picture, these are experimental people, okay? So again, 3 students and a postdoc. Now, these aren't people from a different planet that don't talk to each other. We actually do this because we want them to work together. We maybe want to predict something from our computational work that we can then test with an experiment. Or if we get to a roadblock and we don't have enough resolution with our experiments, we want to dig down more with some modeling and simulation work, okay? And I'll try to give you a feel of that. So I think of myself as a metallurgist. So a simple question you could ask is, what does metallurgy mean? If you go and you Google this or look in a dictionary or something like that, you're going to get a very unhelpful answer. It's going to be something like the science and study of metals. Probably could have guessed that, right? So I want to spend maybe 30 seconds on how I think of metallurgy. What do I think the core sort of way of attacking problems is? So I think we tend to start by this black text right here. We want to understand a basic defect or something going on inside of my material. We want to understand how it behaves, okay? A specific example of this could be that dislocations, a line defect inside of materials. In metals, it's going to control plastic deformation, or the permanent deformation we get. We don't want to stop with just that knowledge. We want to go and we want to learn a little bit more about that. So we might want to think about how microstructure, or all the features inside of our material, affect that mechanism, okay? If I'm thinking about dislocations, I might say that precipitates, or little pieces of a second phase, can act as an obstacle for that dislocation moving through. And of course, I can get more complicated in how I think about that. This is a nice recent example from Dave McDowell at Georgia Tech. They were looking at this is a mesoscale model of little dislocations, trying to move past these second phases. And what's important is that there's multiple length scales at play here. They were understanding what happens on a small scale, so when the dislocation is caught up at every obstacle, but they also have to think about a mesoscale. So there's also this second type of state that they have to worry about when you have a longer spacing between defects. And they were looking at critical stresses there. So you might want to go and calculate, understand, and tabulate all of those things. But again, we want to use this. So what we're going to do is we're going to take this knowledge of a defect, how it interacts, and we're going to then revisit our processing and fabrication. So if I think about dislocations controlling plasticity, I know that precipitates can be obstacles. If I want to make a stronger material, I might go in and choose an alloy that allows us to have many nanoscale precipitates. And this is an example of a copper tantalum alloy. So these circled guys are tantalum-rich particles, and they can give us a high strength. And usually we don't stop there. We'll sometimes want to iterate around this and further understand what happens and refine our theories. Okay? So it's a little bit more information than I study metals. Okay? Now, I mentioned that in my group we do a mixture of computational experimental work. And really what we're defined by is not by a technique. So we don't just have a hammer and we're going to use that. Instead, what we like to do is we like to find interesting problems. We like to come up with a solid hypothesis. And then we figure out what techniques we need to use to attack this, right? And I've just showed sort of 4 different blocks of types of problems we might solve. It's not all-inclusive of everything we've ever done. But in each of these, I've tried to find examples of things where there's computational experimental work going on, okay? And I'm not going to go through them all, but on the top side, something I won't talk about today, we've been studying grain boundary networks inside nanocrystalline materials. So how the interfaces form a connecting network inside. One thing we had to do was we had to figure out how to characterize these. So you can do this in coarse-grained materials rather easily through something called electron backscatter diffraction, or EBSD. But it turns out the resolution is 100 nanometers. Everything I study has smaller grain sizes. So we had to figure out a way to do this through what's called transmission Kikuchi diffraction. So we could go and get, every time you see a different color, you see a different orientation of the crystal, and we could figure out what the grain boundary network starts to look like from that. In the middle, we had to develop some theory. So we wanted to think about breaking up the network, making it hard for cracks to propagate through. So we wanted to think about, rather than just saying something like, I have a certain number of this type of grain boundary, we wanted to think about the connectivity or some sort of metric about how these things connect. And we started thinking about what are called twin-related domains. So it's a whole chunk of material where every grain is related by a twinning operation. Okay? But we've also been modeling this too. So we wanted to understand how these things were affected in nanostructured materials, the dynamics of what was going on. So we did some molecular dynamics simulations trying to simulate cyclic plastic loading. We had to figure out new ways to rip out information from those models. They just give us a bunch of atom positions that could feed in and help us understand these experimental results going on here. Okay? So it's trying to hit a bunch of different things, experiments, theory, and computational work. And you can find examples of the same on all of these. This is an example of wrinkling in films. This is an example of modeling shear localization within nanocrystalline nanowires. And this is an example of studying grain boundary doping in structure. So I don't have time to sort of sit here and drone on for hours about everything we've ever done, show you every piece of data we've ever shown. Instead, what I'm going to try to do is I'm going to pick one story and try to work my way through and show you an idea, give you an idea of how our approach was able to solve an important problem in our field. Okay? And I'm going to talk about a class of materials called nanocrystalline materials. The interest in these types of materials goes back to something we can find in our introductory textbooks. So our textbooks tell us that if we reduce the grain size, make the crystals smaller, our material will get stronger. And this goes back 70 years, right? So these are some early experiments on microcrystalline iron, where Hall found as he reduced his grain size from a millimeter down to tens of microns, he saw his strength shoot up, okay? And this is just a little picture of what a material like that might look like. We might take this, we might polish it, we might etch the surface a little bit so that we can see those just different crystals. Right? And what we wanted to start with, the interest in these materials said, okay, this is pretty cool. I see this curve is going up at a high rate. Let's extrapolate it. And at the time, maybe they couldn't do it. But as we've gotten better at making materials, we could start making materials where our grain size is much, much smaller. So on the right here, this is a similar type of micrograph. So here, wherever we see something dark, that's a crystal of a different orientation. But our scale bar is 1,000 times smaller. Okay? We're looking at a nanocrystalline material. Our grains are less than 100 nanometers. And if we go and we extrapolate out that equation, we're going to come up here and we're going to predict strengths in the range of thousands of megapascals or gigapascals. These are stronger than the strongest steel that we've sort of ever engineered. So from an engineering perspective, this is interesting to me. I want to think about looking at great properties. But there's also some fun science there. It'd be boring if everything just followed that trend. Instead, if we look at real data, so this is hardness, you can think of it as just a stand-in for our strength, we see that it does increase, but at some point, it plateaus. And there's some studies that have even seen that the strength goes down. Okay? The scientist in me sees that and says, there's something fun scientifically going on. Whatever was behind this original equation is starting to break down and fail. There might be some new mechanisms, right? That first place a metallurgist starts. All right. So we were interested in nanocrystalline materials. Turns out they're plenty strong, but we wanted to start solving some of the big problems. And the biggest problem you have there is that although these materials are very strong, they tend to have limited ductility. So this is an example of experimental data, making a nanocrystalline film, pulling on it. You get nickel that instead of 100 megapascal strength is 1.5 gigapascals. That's great. But that doesn't look like the stress-strain curve for a typical metal we're used to seeing. We're used to being able to pull on something. It yields, and we can stretch it out. This is how we form many metals. We make thin sheets of them by plastically deforming them. Okay? But the real important thing is that this material doesn't show a lot of ductility, but it hasn't become a ceramic. Okay? Another class of brittle materials is you can think about taking a plate. If I bend it, it's just going to shatter and break everywhere. These materials aren't quite like that. If we go and we look at the fracture surface of a sample something like this, we're going to see fracture characteristics that still look like a metal. So they have something that we call a dimpled cup and cone type fracture. So a colleague of mine that I collaborate with nowadays, Brad Boyce, termed this in a way that I thought was very helpful. He said that nanostructured materials don't have extrinsic ductility, so they don't show a lot of strain on this x-axis here, but they have what he called metallurgical or intrinsic ductility. You're still having plastic deformation on a local scale, but it localizes early. So that's the major problem we have to solve. Okay? So when we do this, we have to keep a few other things in mind. We have to be able to retain the strength of this nanocrystalline material. There are plenty of ways that people have come up with wacky ways to improve the ductility of nanostructured materials, but they always come at the expense of strength. If we think about this, we can start with a sort of master plot. Take a bunch of experimental data for copper, and we're going to plot elongation to failure. So the higher I am, the more ductile I am, versus strength. So the farther I am to the right, the stronger I am. And almost everything falls on this traditional envelope. Okay? This has been something that people have been after for a long time. There's different ways you can do it. We can start to think about some of the ways people have moved past this. So nanostructured materials would be right here if I just made them and tested them. So people have moved a little bit beyond that envelope. You can do sort of very specific things. You can make what are called nano-twinned metals. So here you're thinking about having a lot of a certain type of grain boundary inside of your system, a certain type of boundary between crystals. Or you can think about making what's called a bimodal grain structure. So you have a mixture of two populations, one really big and one really small. And you can convince yourself that you get outside that envelope, but when I look at this data, I still see that same trade-off. I still see that I have to pick something, albeit a little bit better than I had before. People have even thought about different ways of organizing inhomogeneous grain sizes inside of the material. Rather than just having some random mixture, you could think about making some component where the inside of my sample has big grains, and they gradually get finer as I get near the surface. And some people predicted that these might be better than before. And if you look at the data, they're a little bit better. They're these red points right here. But even within that data set, I'm still picking which one do I want to optimize. Okay? And finally, you can think about even changing your microstructure as you deform. So if you make very pure nanostructured materials and you pull on them, you'll find that the grains coarsen and grow during that deformation. And you can go from something that has very little ductility to something that has quite a bit of ductility. All they had to change was reduce the number of impurities in their sample a little bit. But still, my material is much weaker in this red case. Okay? So that should tell us something. We're not going to change grain size and just fix this. Okay? We need to find a different knob to turn that might be able to let us tune how hard it is for these materials to fail. And finally, there's another critical issue that we have to consider. And this is the limited stability of these microstructures that give us these interesting properties. So this is from this plot on the left here is from a very early example of inert gas condensation of copper. And these scientists went and created and deposited some samples, went and used X-ray diffraction to measure what their crystal size was, and they found that they were well below 40 nanometers. So they were excited. I know a few of these people. They're German, so they probably went out and got a beer to celebrate, right? And when they came back the next day, they were worried, because then they measured their sample again. They saw that their grain size had gotten a lot bigger. These data points showing grain size versus time are just at ambient temperature. Set it on the lab bench, go celebrate, go skiing, whatever you want. Your sample doesn't remain the same. That's a problem. Right? You can see this in other examples. This is an example of a deposited copper film. Again, all these contrast points are little small crystals inside of our sample. If I heat this thing up just a little bit, 45% of our melting point, so not very high, I can see that these grains very quickly get much bigger. And I'm going to lose that strength that I care about. So we're not going to focus a ton on this, but this is a consideration, and alloying your material seems to be the answer. So you want to put in a second element that goes to the boundary and stabilizes that microstructure. Here what we're showing is grain size as a function of homologous temperature. So as I increase my temperature, my grain size is going to go up. So I'm going to get some growth. This red curve is for pure copper. So it's showing that I don't have a very stable material. I only go to 20% and my nanostructure goes away. Okay? As these curves get pushed out to the right, I'm getting better and better. And to get that, I'm adding in second elements that segregate to the interfaces. Okay? And we'll come back to that a little bit later. So what I have is I have one major problem. I have a lack of ductility in my nanostructured materials, but I have these two qualifiers. I need to make sure that whatever I do, I retain the high strength, and I keep that thermal stability, or I have some thermal stability that I need to care about. So because I said we want to start by thinking about mechanisms, let's go through each of these. Right? So the strength of nanocrystalline materials is still controlled by the movement of those line defects I mentioned called dislocations. But the dislocations start to interact a lot with the grain boundaries. Okay? They have to be nucleated from some grain boundary site, and as they're moving across, they get pinned at boundary sites as well. This is showing a dislocation in a simulation bowing out and getting stuck up at those side grain boundaries. Right? So if I want to think about strength, I need to make sure I strengthen the grain boundary pinning and nucleation sites. In terms of stability, a simple way of thinking about coarsening of your microstructure is you can think about the velocity of a boundary and break it down into the mobility, which relies on the diffusion that you have, and the driving force. So grains get bigger because they want to get rid of defects, lower the energy of the system. Right? Now, if I want to combat this, make a more stable material, I need to change something about my material so I can reduce the grain boundary energy or reduce the mobility. And often I said we're going to do this by doping. The ductility was a little less well understood when we started, but we made a hypothesis. We figured out that it had something to do with what these dislocations do after they get to the other side of the grain. Right? This is a very nice molecular dynamics example from Eric Bitzek and Helena van Swagenhoven. What they did is they made a nanocrystalline sample in the computer, and they took inside one of those grains, they put in an artificial dislocation loop, they loaded this thing up and saw what that loop did and how it disappeared. Okay? So they're basically getting rid of the nucleation and pinning, just studying the absorption. And if you look at this top figure, you say, the dislocation's there, poof, it's gone. But something important happened when that dislocation got absorbed. We changed the boundary structure. If we look a little bit more closely before deformation and after, and we look at the local stresses. The big benefit of computer modeling is we can go and look at atomic scale features that we can't see in an experiment. They could see that one of those boundaries started having these bright spots. So these are regions of high hydrostatic pressure. These are the types of stresses that are going to open up cracks, right? So you want to delay crack nucleation at the boundary is the sort of critical example. And hopefully you kind of are a step ahead of me and can figure out where I'm going with this. There's a common theme in all these things. We need to think about the grain boundaries in these materials. We need to think about their structure. So we started going after this problem, or trying to find a solution to this problem, by thinking of boundary state as a tunable variable. So we thought that not all boundaries are perfectly alike. There must be some ability to change what they look like. And it turns out that we can easily see this by just looking at a given boundary in a nanocrystalline material. On the top here, I have a high-resolution TEM image of a grain boundary. So crystal 1, crystal 2, the boundary in the middle. And what these researchers did is they went and they plotted what you could call grain boundary dislocations. So just plotting, using that same idea of a dislocation to plot where we have some defects in the boundary structure. And everywhere you see one of these, this is a certain amount of disorder, if you think of it that way. On the bottom here is a theoretical prediction. So it says if I took two crystals with the orientation of grain 1 and grain 2 and put them together in the lowest energy configuration I could find, where would I have to have grain boundary dislocations? In some of these places, you see the same defects. So you see this little collection of 2 there. Something very similar is right up there. But there's other places where you see extra defects in the real material. Okay? There's an extra little symbol there that isn't down in this boundary. So our real materials have more disorder or more defects than they need to. From a modeling perspective, you can also think about this as I put 2 crystals together. I can cut my crystal, take it, I can tilt it in different directions, and slap it together. But that's not necessarily the lowest energy configuration. If I want to find the lowest energy configuration, I'd have to shift it around in certain directions and maybe even think about adding and taking out atoms to find the lowest energy state. Okay? So this extra disorder happens when I just slap it together. I can relax it and find a lower energy state. So to test this, we took some nanocrystalline nickel tungsten films. We wanted to see what effect this would have on the mechanical behavior. We took and we made a little microcompression pillar in these samples, and we smushed on them. We see that our materials are very strong. They have GPA level strength. But as we load this, we start to see some plastic flow, but eventually we see a burst. This doesn't happen because I stopped my test. It happens because the sample violently failed. If I look, the samples shear off and deform in this catastrophic way. Okay? So one way I could change the state of the boundary is I can try to find my lowest energy state. The way I'll do that is I'll heat my sample up just a little bit, not enough to change what my microstructure looks like, just allow for some diffusion and get rid of those extra defects. And when I do that, I see very different stress strain curves. Okay? I see that my material is stronger and that these localization events, or the end of these curves, happens much earlier. Right? Turns out you can also do this by changing the chemistry of the boundary. This is an example from nickel bismuth. And what these researchers found is they were trying to explain a long-standing embrittlement caused by being in the presence of bismuth, and they found that you get this bilayer segregation pattern. The bonds are very stretched, and it's very easy to run a crack up through that grain boundary. Hopefully you're scratching your head and saying, okay, boundaries matter, but what did I do? I just made it worse, right? I went from a not great material to a worse material, okay? But I can bounce back from stuff. So I said, okay, that's interesting. We learned something. Ordered is worse, so would that suggest the other way? That we should move to the right on here. We should add more disorder, and maybe that will help solve our problem. And there weren't direct tests of this, but there were a few sort of example materials that suggested this might just be a path to go down. So there were some model films made by Morris Wong at Lawrence Livermore National Lab, where he was depositing nanocrystalline copper layers, and every once in a while he would interrupt this and put down a copper zirconium layer that underwent solid state amorphization. So these layers are very disordered. Okay? And what they found when they pooled on these films was that their copper zirconium sample with those amorphous films could be pulled out to much larger strains than the pure copper sample. Okay? So the question we really wanted to ask was, can disordered or amorphous grain boundaries solve this problem of premature failure? Okay? And to test this, we jumped into modeling. So we have a hypothesis. We think that this might work, but we want to understand the physics of this and understand how this might happen. So we wanted to create an atomic scale model of the critical event. So you could think about doing this by brute force. Make a model that looks exactly like my experimental sample. That's difficult. You might not be able to have enough grains. You might have a lot of stuff going on. You can't really isolate the thing you want to do. Instead, I want to think about the critical mechanism and make something simple that lets me isolate one type of behavior. Right? So what we did is we started by creating a very simple sample geometry. 2 grains, the red and the blue. Okay. And what we have right here is a boundary that we chose just so it's very hard to have direct transmission through a boundary. Okay? We made it so that the resolved shear stresses are minimized on the slip planes in this boundary. Right? And then what we can do is we can go and operate an artificial source of dislocations inside of that sample. What we actually do is we take 2 rows of atoms and we just shear them with the type of shear you would get with a dislocation. This is total make-believe. That doesn't happen. But that doesn't matter. It lets us get the critical features that we want. If you look at this sample, you can see a little red line. The stresses are outrageously high at that source. So that source is fantasy. But I don't care. I'm not looking at the source. What I'm using it is to create defects and then look at what happens when that little dot right there moves out and interacts with that boundary. And there are some details and specifics about what we were doing. There's often some limitations on these types of models. We can only model a certain number of atoms. We can only model a certain amount of time, which means we have to use relatively wacky strain rates. But it lets us sort of isolate the important features. And most importantly, it lets us change what this grain boundary structure looks like. So we can go in, pause everything, stop, take the boundary, meld it down, freeze it in, give it an amorphous structure. And we can do that with different thicknesses. So this is the same type of sample. Here's a little radial distribution function. You see these sharp peaks? That's because we're inside of our crystal. All the atoms have long-range order. But in the boundary, it has this wavy type of lack of long-range order. So I made an amorphous film there, and I can change the thickness of it to whatever I want it to be. Right? So I'm going to show you some movies of this type of deformation. So here's the first is just nothing special at the boundary, what we could call an order. There's no doping. There's no amorphous boundary there, just a normal 2 crystals smushed together. What we're seeing is the defects. So the colored things are the defect atoms. And after I absorb about 2 dislocations, I see this crack open up very easily. That's consistent with what we know about nanocrystalline materials. They're very, very brittle. I can start to add an amorphous film, look at how I'm shooting dislocations into that boundary. I can see that I can absorb a few dislocations, and eventually I form a crack there. And I could keep doing this, look at different thicknesses. I could even change the chemistry if I want. And this is just an example, a thicker boundary. I'm still absorbing lots of dislocations. Eventually, you're going to see a little tiny crack open up there. But a real important thing will come back is that there's this brightness, this red you see in this boundary. Those atoms are colored according to their atomic strain. So what we're seeing is that strain is shared inside this thicker boundary. We can quantify these things. We're doing it at very low temperature, so we want to do many, many simulations. So in this case, we did a dozen or so per thickness of the amorphous intergranular films. That's what I'll call them from now on. And what we see is that our number of dislocations absorbed before we crack goes up as a function of the AIF thickness. So if I have a thicker amorphous film, I could absorb more dislocations before I crack. If I want to sort of extend that to what that would mean for bulk properties, it would mean I can have more plastic strain before I can crack. We also see it can track how this affects the propagation of that crack in the early stages of its growth. If I want to look at when that crack first forms and how fast it grows, I can plot the crack growth rate as a function of this amorphous intergranular film thickness. And again, it turns out that our crack growth rate is very high to begin with. I had to actually create an inset to show what it did at the low strain rates. But this rate drops down dramatically as I start to add this disordered boundary film, although it saturates at some point. It doesn't keep going down forever. But the other nice thing about these types of atomic scale models is I can understand why this thing might work. Okay? So this is just a plot showing 2 different strain values. When a dislocation comes into a boundary, you're going to find this little bit of free volume or empty space, right? Now, what needs to happen inside that boundary is things need to rearrange, fill that. In this case, this was a happy event. The atoms rearranged, they filled in that empty space, we're all good. We can keep going. The problem is when that doesn't happen efficiently, this can be how we can start to form cracks, and then those cracks can grow. The amorphous film is very different. When we see a dislocation first start to come in, we see some brightness here. So again, this is local shear strain that we're getting. But we also see some bright spots further on into the film. So these are what people sometimes call shear transformation zones in a glass. So you're getting a local rearrangement of the atoms inside the glass. And as this process keeps going, we go to higher strains and more dislocations coming in, we see the development of this region here that's sharing the burden. Okay? Rather than some thin boundary having to absorb all the damage, we're sharing it inside this thicker grain boundary film. And we can do something similar with crack growth mechanisms. We can plot how the crack is. This is just showing, we're isolating where the crack is at any given time. You can obviously see that the cracks are smaller in the thick amorphous intergranular film. But we can go and look at atomic stresses. So we know that normal stresses open up cracks. And in the case of the clean boundary, we have high hydrostatic stresses or normal stresses around that crack, and they're going to act to open it up and let it grow. On the other case, the stresses, although high at individual atoms, they're much more random in this amorphous intergranular film. So it's sharing that damage in a more sort of homogeneous or way that dissipates it over a larger region and doesn't lead to stress concentrations. So I like that we can model this. I like that we can understand it. But at that point, we didn't have a way to extend this and apply this to real materials. So we wanted to see how could we add amorphous boundaries to real materials using some interesting material science concepts. And we took great motivation from people working in ceramics. So these authors were studying grain boundary mobility in alumina, so a very classical sort of material. And what they found, though, is they looked at a bunch of these alumina materials with slightly different amounts of dopants in them. They got 6 different regimes of grain boundary mobility. So the data fell on these 6 different lines. And their hypothesis was that each of those lines, the boundaries had a certain structure. They were electron microscopists. So they went and they dug in and looked at the inside of their samples and found that, sure enough, their hypothesis was right. You can get everything from a clean or normal grain boundary. You can get layered structures of dopants. Here, the atoms are appearing brighter because it's a different chemical species. Or you can get discrete films with an equilibrium thickness. And finally, if you keep going, you can get very thick, sort of bulk-like phases that happen to nucleate at the boundary. Right? On the top, these are showing examples in alumina. On the bottom, these are other types of examples in metal. So the same sort of class of defect. And what was sort of profound about what these authors did is they started calling these something called complexions. So they were thinking about this being something we could analyze with equilibrium thermodynamics and predict. It's a lot better than just random things happening, right? And in my case, I'd be interested in this nanolayer type of film. What I want to happen is something called grain boundary pre-melting. This is an idea that interfaces should melt below the bulk melting temperature. But it turns out that in a single component system, it's really hard to get this to happen. You have to get almost at the melting point, so close that it's meaningless practically. Okay? But if we dope the boundary, if we change what the chemistry is of that interface, we can make that pre-melting transition happen earlier. And people have started to study in the last few years the thermodynamics of this. This is a normal phase diagram. So the blue is the normal phase diagram. And these red lines on here are showing the thickness of amorphous films. You can analyze this by thinking about we're going from one interface with an energy penalty to 2 interfaces and something with a bulk penalty. That amorphous film has a bulk penalty. And you could come up with an expression that says that the thickness of this film is going to be inversely related to the volumetric energy penalty of having that amorphous phase. Okay? We also can see from this plot that the higher temperatures we go, we should expect thicker films. For me, this tells me I want something that there isn't a high penalty. I want a good glass former. Right? So what we did is we looked at the metallic glass literature. We found the best binary metallic glass you could find. It was the first one they discovered, copper zirconium. This is just showing bulk metallic glass is sort of a nebulous definition. It just means we can cast it into a certain width. Okay? But it has something to do with how hard it is to crystallize that glass. So we wanted to make a nanocrystalline metal version of this. So we did mechanical alloying to make nanocrystalline alloys. We can make two different versions. We can make pure copper. So we just put copper powders in. We beat them up until the grains get refined. We can talk about how that happens later if people are interested. And we can get a nanocrystalline powder. At the same time, we can make a copper zirconium version. We mix together copper powders and zirconium powders. We're going to get solid-state mixing of these. And we're going to end up with a nanocrystalline powder with zirconium mixed everywhere. All right? And the idea here is we can heat this up, allow sort of thermodynamics and energy balances to take over. The zirconium is going to want to segregate out to the boundaries and create something where the interior of the grains are pure copper and the grain boundaries are a mixture of copper and zirconium. On the bottom here, I have electron microscopy images of these things in real life, not a dumb schematic that I drew, right? So on the left here, these two, you can see this is pure copper, copper zirconium. The grain sizes are roughly the same. They're 30 nanometers. If I go and I do a line scan inside my electron microscope, I get these random spikes where I have zirconium, but they're not preferentially at the boundary. They're sort of mixed in randomly. If I take this thing and I heat it up, and then I go and inspect my material, I find that I get these very distinct peaks of zirconium at the boundary, only pure copper inside the grains. It's not my main focus, but it turns out that doping the boundaries with this zirconium increases the thermal stability. These are two samples annealed for the same amount of time at 950 degrees C. This is the pure copper. So again, the contrast marks grains. These grains have grown to the micron range. They're not stable at all. The copper zirconium has stayed below about 50 nanometers. That's plenty stable for what I need. If we look at this in more detail, do more extensive grain growth studies, we can find that even if we heat this to that 950 degrees C for a week, so it's important to mention what that temperature means. The temperature by itself doesn't mean anything. What matters is it is for that material. This is 98% of the melting point for my material. I leave it there for a week. My grain size is still about 50 nanometers. So that's very stable. And I can explain why this happens. I can do some atomistic modeling and show how the potential energy of my system drops as I go and add increasing amounts of zirconium to the system and those segregate out to the boundaries. I'm not showing it here, but I can track how that segregation happens too. Now, I'm also probably getting some kinetic sort of effect here. I have a large spike in composition. And if I think about moving that boundary along, I would need to drag that composition along too. So there's both things at play here. But as of yet, I haven't said anything about having disordered boundaries. So we wanted to test this idea of could we form disordered films at our boundaries. And the way we did this is we made two sets of samples. We heat them up to this very high temperature. The reason we did this is because those models told us that high temperature would give us thicker films. If I want to see this experimentally, I need the thickest films I can get. I need it to be as easy as possible, right? So I heated these two sets of samples up to 950 degrees C. One of them, I dropped it in a water bath, quenched it down within a second. The other one, I slowly cooled down over an afternoon, right? So a few hours to cool it down. And then I took both these samples, and I went and looked at the boundaries. I didn't look at anything, right? My students looked. When you look at the annealed and quenched samples, so the quenched ones, we freeze it in, you find these nice grain boundary films. So they're disordered. We don't see these repeating patterns of dots that we got inside the grains. We see these throughout our sample. But one thing that's interesting is we find that there's a variation in the thickness of these grain boundary films. They're not all one thickness. They're different thicknesses. Okay? And we can contrast that with the case of a sample that was slowly cooled. I'm showing you one boundary. That's not proof, but we have to go look at 50 boundaries. We never find these amorphous intergranular films inside of our slowly cooled sample. Now, this isn't where this ended, and I'm not going to go through all of these, but we were left with a number of questions. We wanted to know why we got a variety of thicknesses of these films. We wanted to know how were these different from bulk glassy phases. And we wanted to know if we wanted to optimize this effect, maybe get thicker films or have them happen at a lower temperature, how could we change our alloy composition? And these are three places where atomistic modeling was incredibly helpful. We found that the thickness variety came to the fact that different boundaries have different energies and different tendencies to segregate. So the sort of enrichment at a given boundary is not equal for every boundary. We were able to see that for very thick films, the center looked just like a bulk glassy phase, but these regions near the amorphous crystalline interface had different short-range order. So this is something that we can't really study experimentally, but computational work let us do it. And finally, we're starting to extend this out to ternary alloys and different collections so that we can get really thick films, really increase our ductility of our material. What I want to show you to finish off this story is we wanted to go and prove that this was actually a beneficial feature. So the way we did this is we tested directly on the powder. So we made some small-scale compression samples on powders. We went and smushed on these. We could go and characterize what the stress-strain response and compression looked like, see that our strength was actually increasing as we went from pure copper to copper zirconium with ordered boundaries to copper zirconium with amorphous intergranular films. And we could also get this hand-waving finding that the ones with ordered boundaries crumpled and cracked, while the ones with amorphous intergranular films did not. Finally, we could do bending experiments to see how these things failed. So this is a pure copper pillar. You'll see a crack open up very early and just sort of rip through the sample as we continue to push. If we push on one of these copper zirconium samples with amorphous intergranular films, the student went and got a coffee or something. Yeah, there he goes. He goes again. So he's able to push this thing over, and we don't see any cracks forming at the base. We're really able to deform this out, get lots of plastic strain at the base. And we can go and analyze these, estimate what our strain to failure is, and go and plot back on that master curve. So this is our pure copper, this is our copper zirconium, and our copper zirconium with amorphous intergranular films is the best one. So we're able to get high strength and reasonable ductility. And we feel reasonably comfortable in this for two reasons. First is that this pure copper sample falls where uniaxial measurements have come before. The one sort of weak point of this is this bending is not the perfect way to test this. But I have results I can show people if they're interested, where we're doing in situ tension of these and seeing that they're much more damage tolerant as well. Okay, so I have a few more minutes. And what I want to do is just show you a few interesting results that we're really excited about that involve some of these open questions we have with these types of ideas of defects in materials stabilizing different structures in different localized phases. I'm not going to go into all these things, but we're also looking at fun things like radiation damage, how we can consolidate and make big bulk pieces of this, and then also things like how can we optimize our chemistry and how can we apply this to different material systems. So I showed you an example in copper. We've actually extended this out. You give me a metal, I can tell you which system to choose. Okay? But the thing I want to finish with are can we get these localized phases at other types of defects? And what we're really inspired by is some recent work from Dirk Rabe's group in Germany. They do this really beautiful materials characterization. They make these thin little needles of material. They can do transmission electron microscopy and pick out all the defects. And then they can take this thing and do what's called atom probe tomography, where they rip all the atoms off and find their chemical composition. And they can correlate these things. And what they found was this, in this iron manganese alloy, they would find that along the dislocations, they would get this enrichment in the manganese content, where they would have, if they cross the dislocation, a peak, and as they go along the dislocation line, this undulating composition. They were interested in the fact that this seemed to be related to strain aging, okay? But they didn't dig in anymore. And part of the reason is this is about the best they could. They had a hard time saying exactly what was going on. We wanted to do atomic scale modeling to understand how these transitions happened. Now, one sort of downside of atomic scale modeling is you're limited by the potentials you can use for molecular dynamics and tools like that. Turns out, they studied iron manganese. We didn't have that. There isn't a potential. If you want a potential, you can spend 3 years discovering it, or you can be creative and you can look for a material system that's kind of similar and has some of the same aspects. So we found a nice potential for iron nickel. Turns out that this part of the phase diagram where we're working looks very similar. And I'm going to show you some results where we went and made a simple model where we have 2 dislocations in a cell. And we're going to look at what happens when we dope that with nickel. So it's pure iron to begin with. It's a body-centered cubic material. And we're going to dope it with nickel. We're going to use what's called a Monte Carlo molecular dynamics model. The basic idea is that we get chemical and structural relaxation of all the atoms. And we're going and finding an equilibrium state. So we start to see if this is a relatively low composition. So it's all BCC here. We're colored according to our crystal structure. But we start to get high concentrations of nickel near the dislocations. And as we increase the composition, go to 2%, 2.5%, we start to nucleate out second phases. All right? And the most important thing is that these second phases seem to be some blob of this red, which is a B2 structure, with a little bit of green on the inside, L10 structure. So these are both chemically ordered phases. So the B2 structure is BCC, just like our iron by itself, but it has a 50-50 mixture of iron and nickel. The L12 structure is a face-centered cubic structure with a 50-50% of iron and nickel. Okay? And I'm going to jump forward to the fact that if I look at my chemical composition profiles, I can see that my models look very similar to their experimental results. But there's one big difference. When they looked at their data, they found that their compositions at these dislocations matched up exactly with the phase diagram. And they had some evidence that there was some local FCC structure. So they just said, hey, it forms that L10 FCC structure, we're done. Okay? But we're seeing something very different. We're seeing two-phase coexistence there. And most importantly, we're seeing this outside wedge of this B2 phase that doesn't show up anywhere on this phase diagram. It shouldn't be a low energy state. Now, the first thing you could say is, well, you didn't find a true equilibrium state, but it turns out that's not true. We could keep going, run these simulations forever. We find no change in the proportion of these different phases. What we really need to do is understand the energetics and the thermodynamics of what's going on. And what we want to do is compare and contrast the L10 and the B2 phases in this case. So we can start by thinking of the bulk energies. So we can go and we can calculate, using this potential, what is the energy of 50% iron, 50% nickel for 3 different crystal structures. This is also a beauty of modeling. We can do fantasy situations. It doesn't matter what the preferred energy is. I can put it in that configuration, figure out what its energy is. And what we see, and we can test things like this is a solid solution. So it's a BCC structure, but the atoms are just randomly mixed. We can look at that B2 structure, so an chemically ordered BCC structure, or that L10, so a chemically ordered FCC structure. And not surprisingly, this is what the phase diagram tells us. It tells us that the energy is lowest for the L10 structure. So the bulk energy is larger for this B2 structure. But we're not thinking about a bulk phase diagram. We're thinking about something happening very locally near a defect. So we need to think about the interfaces that are created as well. So we can go and we can estimate this and try to figure out what the range of interfaces would be. When we have a B2 structure inside of our BCC, we can have coherent interfaces. They're very low energy. And we can estimate that by modeling a few of the sort of options that you would have. And you would see that you're going to get something like 1/10 of a joule per meter squared. Okay? On the other hand, if we put something that's FCC inside of a BCC structure, we need to have incoherent interfaces. And we can find some bounds by that by looking at these very well-known types of incoherent interfaces and figure out that we're about an order of magnitude higher. So our energy penalty is about 1 joule per meter squared. And then we can use these to our advantage and go and sort of predict and plot what would the energy be needed to nucleate a spherical precipitate. We can create something that looks like this. This is the energy or the work we need to do to create a precipitate of radius r. Okay? So these both go below 0 when they get big. And if we get beyond a few nanometers, the L10 wins. So that tells us the bulk phase diagram isn't completely made up. It's actually right if we have big particles. But it misses what happens in this local region. In this local region, the energy for the maximum right here is 3 orders of magnitude lower than the maximum for the FCC structure. And we can sort of think about that even further by thinking about the probability of nucleating each of these phases. It's going to be exponential with temperature. And the probability of nucleating a B2 over an L10 phase is incredibly high. So this is a sort of plot on 0 to 1. I'm going to take and put this on a log plot. So we get 10 to the 4 here. We get 10 to the minus 100. These are not even rational numbers to really be thinking about, right? It's just showing you that it's so low, the probability of nucleating L10. So what is actually happening here is we first nucleate out this metastable phase. And when this metastable phase is there, we can then precipitate out this L10 phase. And then this thing can grow. And we can minimize our energy there. And then if we look at a different way, not down the dislocation core, but along the dislocation line, what we're getting is something that's similar to spinodal decomposition. We get high composition regions and low composition regions. And those high composition regions are where we get the precipitation of that new phase or what can be called a linear complexion. And the reason this is important is if you understand the details of some sort of phase transformation, we've been able to go, and I won't show you an example, but we can make something like a phase diagram near these defects. So what processing conditions, what temperatures, what chemical compositions, what pressures do I need to be able to make these things in real materials? That's how something like this becomes useful. And we've been able to see it in multiple material systems. So we're writing a paper on a range of BCC and FCC systems. We can see these nanoscale precipitates all along a line restricted to the dislocation. We can see it on the other side of that same phase diagram in a nickel-rich side. But we also can see layered structures where segregation of stacking fault causes a transformation, and even precipitation from partial dislocations. One important thing is that the defect survives in all these cases. It doesn't destroy the dislocation. The dislocation's there, just some phase is localized near it. Now, you can also look towards what you could call defect assisted precipitation. So our local composition gets high, and we just get a bulk phase that comes out too. And that destroys the defect. Might be useful in some situations, but it's fundamentally different than maintaining the defect there. Okay, with that, I'm at the end of my time. I think I'm roughly right on time. But I want to leave you with just a few take-home points from the talk today. So one thing we found is that these structurally disordered or amorphous grain boundary complexions are beneficial for both the mechanical properties and the thermal stability of nanostructured metals. I hope I also showed you some places where computational techniques can let us study this with great precision. Okay? It's not that computers are good and experiments are bad, or experiments are good or computers are bad. It's that these things complement. And atomistic and other types of computational techniques let us isolate things that we couldn't study experimentally. We can look at individual events. We can study small atomic scale changes in grain boundaries. We can look at new alloys. We can do all kinds of things and make predictions with these sets of tools. And we were able to do that and extend this idea of complexions near defects to dislocations. And we're currently looking at how we can affect mechanical and functional properties with that. And of course, I thank my funders, the Army Research Office and the Department of Energy. Hopefully I can take any questions, and thank you very much for your time. Professor Baker?
Thanks for the interesting talk. I'm curious about your modeling about this dislocation behavior when it meets the small grain boundary. So if you further extend your model, broadening this offers there, does it converge back to the behavior of the static glass, or is there an operator somewhere in between mechanics?
Yeah. So I'm just going to reiterate your question just in case people didn't hear it. The question was, if we made the boundaries thicker and thicker and thicker, would we go back to the properties of a metallic glass? Absolutely. So you can think of it almost as a composites problem. We have an issue with nucleating damage at a grain boundary in nanocrystalline. If we have these thin amorphous phases, it can help us absorb that without defects. If those phases became the majority phase, we would start to get shear bands inside that amorphous phase, and we could have localization there. So luckily, experimentally, I can never get to that point. I can't quench in thick enough films. And in fact, this is exactly analogous to what people did in the metallic glass community. The way that they toughened these materials was they nucleated out crystallites that formed dendrites and blocked shear bands from going all the way through the sample. So it's actually quite similar, but you have to stay near a side where you have a majority phase, either nanocrystalline or amorphous. Yep. But conceptually, you would converge at some point. Yep.
So what you talk about is intrinsically sensitive and dimensional. I'm wondering if you could use a atomic layer deposition or something to look at something where you have more control on one of those dimensions and how all this might be affected.
You're absolutely right. So I think there are film techniques where you can make this you can control your boundary structure probably with more control with more precision than we can with these sort of bulk techniques. And I think if you wanted to make a thin film, that would always be the way to go. I guess our motivation was a little bit different here. We sort of wanted, I always had this idea that we wanted to be able to use principles that were scalable to the bulk. And part of that is the focus on structural materials. So turns out that often if you're trying to, part of it you can see from the funding agency, the Army, right? They want me to make strong materials, but they're not interested in microelectronics. They want me to make something that they can then make a stronger tank and keep people safe. So some of it was dependent upon that sort of idea. But I think you could do it in a film form too. Yeah.
And in the same way that your simulations help you understand the physics,
yep.
doing different films might help you understand the physics.
That's true. Yeah, that's true. Yeah.
Question about the localization.
Mm-hmm.
Yes.
Those are two different kinds of metals. Copper is a good metal. I call it good.
Mm-hmm.
Zirconium is a bad metal. They're two different metals.
Sure. Yeah. I know what you mean. Yeah.
Is this localization anything to do with any of application?
I don't think it is, because we can actually get the exact same effect. So the one nice thing about modeling is that I can make a film with 2 grains and an amorphous grain boundary film out of pure copper. I can force that copper to be amorphous, I can quench down with 10 billion degrees per second if I want, right? I can do anything I want in the computer. So I can make it monotonic too. This isn't very practically useful, but I could make that situation. We see the same effect. So it shouldn't have anything to do with the conductivity of the zirconium. The other answer is that molecular dynamics are classical potentials, and they wouldn't treat that very well anyways. so I can also confirm that I wouldn't, if that was important, these classical molecular dynamics simulations probably wouldn't capture it very well either.
How do you go about using the material for separation of the model?
So I think there's different ways you can do it. I can imagine a scenario where if I take that example I just talked about with the dislocation linear complexions. So we're actually using that to predict the processing conditions through which we can go and study these things experimentally. Okay? So we can make a phase diagram, figure out the processing conditions to do that. I can imagine also going the other way. So if you know you have a certain type of interface inside of your alloy, and you could go and get a reasonable amount of characterization, you can then study how that type of interface responds. So, when I go and I do a TEM sample, I can go and find the structure of an interface, but I don't know how that individual interface will respond. It's almost impossible to test that. I know how the aggregate of my sample responds, but if I wanted to directly grab that, I could do that. So I could use that to choose what I model, or use that to choose what I make. Those are, to me, the most obvious sort of directions of having these things work together. And often the choice becomes, what's the unknown? What's the bigger problem you have at the moment? Yeah. So I think I tried to, sorry, I didn't need to go back. But this is almost what you're talking about, right? The fact that their structures are similar with a little bit of elongation. Right. Yeah. Yeah, so it would be if there's some sort of deformation or elongation, which part of was why when we did these calculations for the energy, we did it so this is atomic volume. So effectively going this way would be, you could stretch it in different directions and shear and do all kinds of things. This was just changing the atomic volume of the simulation cell. So what we were doing was trying to get some measurement of that. And even if you deviate a little bit from that parameter, you're still going to be the lowest energy state. But you're right, yes. So it doesn't have to be, it might be that it's not exactly at this, it's somewhere like right here. Yeah. That could be true. All right, thank you very much.